Hello and welcome to this NPTEL MOOC on Applied Electromagnetics for Engineers. So, most of us are introduced into this world of electrical engineering by a subject called as electric circuits. If you remember what a circuit is a simple interconnection of components, right, or circuit elements. You are familiar with circuit elements which are passive or active. Passive circuit elements such as resistors, inductors, capacitors, transformers. You can take these different elements, connect them in a way you want and then create a circuit, right. You can also take and connect a few of active elements such as diodes, field effect transistors or BJTs and so on. You can connect active and passive circuits together in order to form whatever the functionality. When you connect these elements, right, I mean you study these elements in the form of circuit theory, you have almost never encountered anything about the behavior of a wire. So, let us say you have a resistor here and you have a capacitor here and you want to connect this resistor and a capacitor. The way that you would connect would be to take some wire and then you just connect the wire, and you want to implement these circuits on a breadboard or on a printed circuit board. You would place these components at appropriate places and then just take a piece of wire and connect it. In fact, you might be remembering, if you remember your lab courses, that when you connect two elements by a wire, you do not normally you are not concerned about the wire length or the wire shape. Most of you would have connected it in the form of a bent wire, but you do not worry about what should be the degree of the bend, what should be the angle, how much should be the length, should I twist it, should I not twist it, because sometimes your wires do get twisted, but none of this would have mattered to you while you are constructing these circuits and making experiments in the lab and performing experiments in the lab. You would be very surprised to learn that a simple element such as a wire, which we take as nothing but a connection between two elements or two chips or two modules on a larger motherboard or a daughter board structures, can actually generate lot of problems for you. It can give lot of problems for you, because a wire at certain operating conditions is not just a wire, but it will have its associated inductance, capacitance, resistance and conductance. And that theory is called as transmission line theory, and we will begin this course by studying transmission line theory. Okay. So, as I was saying, we are introduced to circuits, and while we study mathematically these circuits, the interconnection of all these elements, we almost never worry about the wire. Okay. Let us actually look at couple of hypothetical cases. I will give you some sort of puzzles to you, which you would, if you think about it, will tell you the importance of wire in electric circuits, and then why electric circuit theory cannot deal with these effects and why electromagnetics should be involved in order to study these effects. Consider a very simple example. Okay. We have a circuit out here which I have shown. Okay. So, you look at this slide here, you have an circuit shown here, or probably there is not even a circuit here is what you would say, but because I have a source here which I have denoted by some sinusoidal ones, it need not be sinusoidal, it could be just a battery that I have connected. Okay. And what I have, these orange lines are two long wires. So, they are like ordinary wires, but you assume that these wires are about say 10 meters or about 15 meters, right. And this is a switch which I will connect at t equal to 0. So, I will bring down the switch here, and once I bring down the switch, I ask you this question: what will happen? Now, based on what you have studied, you might answer differently. Let us say you will look at the circuit and say, well, nothing should happen, because I have a source and I have a switch. Once I close the switch, there is nothing for the source to deliver the current into, therefore nothing should happen. But some of you might wonder differently. You might remember from physics, electricity and magnetism, that when you have an uncharged piece of wire, when you connect a battery to it, you are kind of charging the wire, right. So, you are kind of transferring charges from the source, which is battery, onto the wire. So, you would say that, well, current flows for a short time, but then the current has to die out, because there is no complete path for the circuit current to flow, therefore current flows only for a short duration of time. You might argue sometimes that the information is not sufficient, because you want to know what is the length and shape of the wire, right. Although that might not be your first answer, but some of you might really wonder and say that the problem statement is incomplete unless you specify what is the length and shape of the wire. Then some of you might also argue, if I replace a battery with a sinusoidal source, that the outcome actually depends on the frequency of the source. So, these are some of the options that you might think over, and what I want to do is to discuss these options one by one and then look at what is the correctness of each option. Okay. First, those of you who would think that nothing should happen, you might be thinking about a circuit, and you might know that in a circuit, for the current to flow, you must establish a complete path. Since in this circuit that I have shown, there is no path, there is no connection of the top wire to the bottom wire, right. So, the path is incomplete and circuit is not closed, hence current cannot flow. And you would also say, I do not care what the frequency of the source is, I do not care what the length of the wire is, I do not care even what the shape of the wire is, because the circuit is not closed, there will not be any current. So, if you actually think in terms of a circuit, you would see that a circuits person, which I am referring to by this cartoon picture over here, what this cartoon picture sees, a circuit person would see, is a battery connected or a sinusoidal signal source that is connected to wires and at the end terminated with a open circuit. Of course, I have not terminated anything, it is just that I have left the two ends as it is and it is an open circuit. Well, current is 0. And those who said that current would flow for a short time, your thinking might have been that from your earlier courses, you know that the wires which were uncharged, right, they had to be charged, and during that time the charging current must flow. But eventually you are right, the charging current cannot flow continuously, it has to stop. At some point it has to stop. So, what is the charging process? What process causes charging of the wire? And how would the charging current look like? Even if it flows only for a short duration of time, what would be the charging current waveform, or the shape of the current waveform? Again, does it depend on the frequency or does it depend on the waveform of the voltage source that you are connecting? These are the questions which unfortunately cannot be answered by circuit theory, and certainly these questions require us to know the length of the wire and the frequency of the source much more than what I have specified here. So, this is a slightly better answer than the earlier answer, because physically it is correct. Once you connect an uncharged wire, the charging current flows, but then eventually the charging current has to die out. Okay. We still are looking at the length and the shape of the wire. So, we this time change this the experimental hypothetical experiment, which you of course also can perform in the laboratory, to slightly different thing. Now, we know from circuit theory that length and shape should not matter, but what I do is I take the same sinusoidal signal source, okay, and then I have a switch here, I close it at t equal to 0, but then instead of sending one wire without any change, I bend this wire before connecting to the resistor. Okay. You can see that I have bent the wire in this way, and what I see on the oscilloscope is that at very high frequency, that is, as I start increasing the frequency of the source here, you will see that the output voltage across the resistor will actually drop to 0. Now, that is something that is very unusual to happen, right. Why should the resistor, voltage across the resistor go to 0? That resistor can go to 0 only when the impedance of this part of the wire would start to look like a inductance, right. The impedance of an inductance would be very high, which would absorb all of the voltage across it, and therefore drop the voltage across R to be 0. In an ideal infinite frequency, the impedance of the inductor would be infinite and no current would actually flow again. So, this is something that you can appreciate, but the question is, how can a piece of wire which I have bent in a particular way can induce inductance or inductive effect? How can a wire act like an inductance? That you have not studied in the circuit theory. It is something that is quite puzzling if you think about it. Okay. What really is happening is that when you see this kind of a wire that is bent, you would see them as an inductor. So, you have to see it at a different element, and you would actually start seeing this one at a different element called a transmission line at different frequencies, right. This is say very high frequencies, this is at mid to high frequencies. Okay. But then the question is, what is meant by inductance and how do I actually calculate this inductance, right. So, we have never been told in circuit theory how to calculate inductance, we are only given an inductor and you want to look at what is the behavior of an inductor. Now instead of an inductor or a wire, now what I do is I take two metal plates. So these are wires that are coming out, but I take two metal plates and then connect this one. Clearly you would know from your earlier circuits courses that two metal plates will have a certain area, and if I fill this region between the two metal plates with some dielectric or an insulator, this arrangement will be that of a capacitor, correct. Again my question is, how do we calculate capacitance? What happens if instead of taking a square metal plate, if I replace them with circular metal plates? Would the capacitance change? Yes, the capacitance changes, but how do I calculate the capacitance, right? So how do I calculate all that? And finally coming down to the length of the wire, in circuit theory the length of the wire, and a fancy word for wire is an interconnect. The word interconnect is quite popular in the microelectronics and VLSI community, where it connects any two modules. These modules could be as simple as two elements, resistor and a capacitor for example, or it could be a driver card, driving a or the microprocessor driving a address driver or a decoder or whatever that is. So it can actually be used to refer to connection between two modules, or it could be used to refer to connection between two elements, and any such connection is called as an interconnect. We call a wire, and we specialize only to wires because in our case interconnects are only metallic wires, okay, at least the ones that we are dealing for quite some time into the course. Our interconnect means only metallic wires, because you can also have optical interconnects. You can just take a optical fiber and then connect two modules, or an optical waveguide and connect two modules, but that is not what we are considering here. What this experiment is trying to do is that I have a source here, I do not have to switch it on at a particular time, let us say it is there on for quite some time, and then I am looking at the output. Okay. Now if I connect a hypothetical oscilloscope here, that is right at the input terminals, I will see a sinusoidal voltage like this, right. So here is a sinusoidal voltage with a peak at some t equal to 0. Please remember this waveform has been switched on quite some time ago, therefore it is actually the voltage that is changing, right. This is with respect to t, and I have placed my hypothetical oscilloscope here. I will also place an hypothetical or a real oscilloscope at this point, okay, and then I look at the voltage waveform as shown by the oscilloscope. Okay. Both let us say are triggered at the same time, I have somehow ensured that they are triggering at the same time, okay. And what you see here would again be a sinusoidal wave, which is what you expect because this is just a wire. But there is one thing that you cannot explain, why is that the voltage waveform that is appearing at this oscilloscope being delayed? A circuits person would simply be confused, why should there be a delay or delay showing up as a phase shift of the voltage waveform at this end compared to the voltage at this end, right. Why the circuit person is confused, why is there a delay? Because the circuits person has been told that the length of the wire does not matter. The circuit model for this scenario, right, I am using a word model in the sense that I am capturing the essential features of this experiment. So if I make a circuit model for this, there will be a source and there will be an oscilloscope. The wire would simply not be part of any meaningful entry out there. So the model does not include wire, or it includes wires, but it treats wires as just an interconnection with zero effect on the circuit. Its only job is to connect the source to the oscilloscope or connect one circuit element to the other circuit element. So this person is confused, and in fact if you start extending the length of the wire, then this delay would be even more. Okay. So that is something that is confused. The reason that happens is because circuit theory is actually only an approximation to the true behavior of a wire. A wire, no matter how short physically it is, it will still have some amount of physical length, and we know that no disturbance that you turn it on at one end of the wire can travel faster than the velocity of light, right. So no disturbance that you create, maybe you are connecting a voltage source which is kind of a physical disturbance because it has to charge the wire, right, and this charging process cannot happen at infinite velocity, in the sense that it cannot happen instantaneously, there will be some delay. At least Einstein tells us that there has to be a delay, and we all know that that is the truth. because lot of experiments have been performed. So, no matter how small the length of the wire is, there will be delay causes phase shift of the current and the voltage waves. Now, you might argue one thing, let us go back to this scenario. Okay. I take a voltage waveform here, instead of connecting this long piece of wire, I simply connect a capacitor, right, and then I look at the voltage across the capacitor and current through the capacitor. Do not ask me how, but we can do that one. Okay. Let us assume that we can do that one. Actually, you will have to use a small piece of resistance to do all that, because capacitors, ideal capacitors cannot dissipate any kind of energy. Okay. So, you will have to use a small resistor, but let us say we use a resistor and we look at the output. We know that in a capacitor the voltage leads the current by about 90 degrees, correct. So, we have that voltage lags the current by 90 degrees, it is the current which leads the voltage in a capacitor by 90 degrees. So, there is a phase shift. Here also you see a phase shift in this circuit, there is a phase shift across a capacitor. So, are not these two similar? Why am I telling you that circuit theory cannot explain this behavior? There is only one catch here. The catch is that I am looking at the voltage at this point of the wire and I am looking at the same quantity. I am actually looking at the voltage at this point of the wire, that is at the one end of wire I am measuring the voltage, at the other end, at the end of the wire again I am measuring the voltage, I am not measuring current. So, I do not actually expect that the voltage will have a phase shift, right. The relationship of voltage current in an inductor or a capacitor is actually for two different physical quantities, one for voltage and one for current. Here the relationship is actually for voltage at one end of the wire to the other end of the wire, right. You might then ask, why am I really concerned about that, why should I be worried about all that? There is a very good reason, if you are especially going to work in the digital hardware kind of a thing. I mean, this is just one example, there are a lot of other examples where this kind of a behavior of a wire will be important in microwaves and radars, but this situation kind of shows you very interesting thing that actually happens every day in your high speed processors, right. Computing devices actually consist of millions of logic gates, and these logic gates are always in the change of in the state of changing, some bit is going from 0 to 1, some bit is going from 1 to 0 on one piece of the output line, and the other output line is going to 0, the other output line may be going to the tri-state, these logic states are all changing at the output, and these switching times are getting shorter and shorter. Today switching times are approximately 100 picoseconds. You can imagine, this is a very small time, right, but the wires that we connect are not able to instantaneously transport this logic state onto the other end. That is, this is a driver and this is the load. Whatever the driver changes, this drive change voltage is happening at 100 picoseconds. Unfortunately, my wire, being a physical length of a wire, cannot really transport that to the other end in 0 time. So, because of that, you will have to deal with the fact that the wire is not ideal, it has delay, and what is the implications of this delay. It also turns out that the wire does more than just give you delay, it also has a inductive and a capacitive type of a behavior. So, we need to understand completely the model of a wire to better represent this situation and to avoid having this kind of a behavior. You can actually see that if I somehow do not manage or match this load and the source, then my voltage waveforms do not come out as expected, but they will have lot of non-idealities or distortions over here. So, one of the objectives of understanding electromagnetic behavior of a wire is to predict and minimize this type of distortions, okay, and we do this by a process called as transmission line, right. Transmission lines, as I said, will we will talk more about the transmission lines. This transmission line will have describe the parameters of this transmission line by resistance, inductance, conductance and a capacitor, and these quantities are all connected to electric fields and magnetic fields. So, if you want to calculate if you want to calculate the inductance of a transmission line or a capacitance of a transmission line, you need to study electric and magnetic fields. Okay. So, in order to understand transmission line parameters, where they are coming from, you need to understand electromagnetic theory. So, just to summarize what we have been saying, a wire is more than just a wire, it can be an inductor, capacitor or a transmission line depending on length and shape of the wire, and frequency of the source. So, electromagnetics is slightly more complicated than just a circuit theory. Unfortunately, ordinary circuit theory cannot account for these effects, and electromagnetic theory is the one that can successfully analyze these effects. Therefore, it is important for you to understand electromagnetics. Electromagnetics is also important in understanding fiber optics, okay, because fiber optics guide light, and light is electromagnetic wave. How would light be guided is given by the fundamental principles of electromagnetics. Electromagnetics is also important to understand the behavior of antennas that are used, and if you look at these two slides which I will upload on the website, you will be seeing lot of applications of electromagnetics. Okay. It is applied in optoelectronics, fiber optics, optical communications, to understand channels, behavior using electromagnetic behavior of the channels and all that. In fact, electromagnetics also gives you a nice philosophical basis for circuit theory, because circuit theory was actually developed as an approximation of electromagnetics. Electromagnetics is also very important for RF and microwaves, as well as for high voltage engineers and for antennas and propagation. So, we will end this module by listing out the textbook. The full syllabus and the lecture plan is given on the website. The textbooks that we will be using is, the primary textbook is Electromagnetics with Applications, and these are other textbooks. I will upload list of references as well as notes on the website. Thank you very much.